On from where we left, and now we are going to look at inductance. Okay, I called it 2.1 because it's a continuation of what we were discussing earlier on. So inductors have a number of response characteristics that are similar to those of capacitors. Unfortunately, we've not discussed capacitors, but what we are saying is that an inductor is an energy storage device. A capacitor is also an energy storage device. So the similarities in terms of how we explain their operation and how they behave when there is a change in current or voltage through them. Those are their similarities. So we use that when we are doing our analysis of the circuits. The inductor exhibits its true characteristics only when a change in voltage or current is made in the network. In other words, we are saying these are energy storage devices can go into what we call the steady-state condition, whereby they will be not exhibiting any characteristics. They will be just passive as they are. But then when you cause a change in the state of the circuit, either by changing the direction of the current or the magnitude of the current, direction of voltage or magnitude of voltage, then you will see the other characteristics of these devices. So an inductor is set up to produce a strong magnetic field linking the unit, whereas capacitors are designed to set up strong electric fields between the plates. So we are saying in an inductor, they produce magnetic fields. In a capacitor, it produces an electric field between its plates. So inductance is measured in henries, H, and we are defining a henry as the inductance of an inductor which establishes a voltage of 1 volt across the coil due to a change in current of 1 ampere per second through the coil. In other words, we are saying if the current changes from 2 to 3 in 1 second, and the voltage across that coil is measured to be 1 volt, then we can say the inductance of that device is 1 Henry, right? Then inductance can also be determined from the physical properties of an inductor. So in simple terms, an inductor is something like this, right? We have a winding around the inductor, right? Right? Then it has a certain length, which is usually the length of the core. Then this will have a cross-sectional area, say A, and it is n number of turns. So the inductance of such a coil, L, is equal to mu. Mu becomes the permeability of this core, n squared number of turns in the coil times the cross-sectional area divided by the length of the coil gives you the inductance of that inductor. So mu will be permeability in Webers per ampere meter. Right, mu Webers per ampere meter, n number of turns, no units for number. Then A cross-sectional area in square meters, right? L, the length in meters, and inductance L will be measured in henries. So that is the formula for determining the inductance of an inductor using its physical parameters or its physical dimensions. Now, if you move a conductor through a magnetic field such that it cuts flux lines, then a voltage will be induced across the conductor. So what are we talking about? We are talking about a magnetic field, right? Then let's say you move a conductor through this magnetic field, right? Then if you had a voltmeter there, you realize that there will be an induced voltage across that conductor as it cuts the lines of flux. There will be induced voltage across that as it cuts the flux. And that is called right. So that's what we talk about in terms of electromagnetism, right? So in other words, we are saying when you move that conductor through a magnetic field and it cuts the flux lines, then there will be voltage induced across it. So let's say if your magnets, north and south pole, very strong magnets, then you move a conductor through it, then a voltage will be induced across the conductor. So this is what we call the generator effect. That's how generators are constructed. Conductors should be cutting flux lines. Then a voltage is established. Then there's Faraday's law of electromagnetic induction, right? In general, the greater the number of flux lines cut per unit time, or the stronger the magnetic field strength, the greater the induced voltage across the conductor. So if the conductor is held fixed and the magnetic field is moved so that the flux lines cut the conductor, we still get the same effect, right? So if a coil of N is placed in a region of changing flux, voltage will be induced across the coil as determined by Faraday's law, and that voltage will be given by E is equal to N d phi by dt. d phi by dt will be the rate of cutting of flux, right? How many flux lines are cut per unit time? That's d phi by dt. That gives us the induced voltage. So that's the illustration. If you're changing magnetic field through a conductor, then you have different values of voltages being induced depending on the values. Then Lenz's law is just saying the induced effect is always such as to oppose the cause that produced it. So Lenz's law will let's skip something there. So Lenz's law will just say E becomes equal to minus, right? That's its effect. Let's look at this. See this equation, right? Then you are saying Lenz's law, it's saying the induced effect will tend to oppose the change that caused it. In other words, Lenz's law is just saying E is equal to minus N d phi by dt. In other words, it introduces a negative sign, showing that the induced effect is opposite the cause. The induced effect is opposite what has caused it. That is what Lenz's law we'll be talking about, right? So the inductance of a coil is also a measure of the change in flux linking the coil due to the change in current. In other words, L is also equal to N d phi by di, right? Don't confuse with E. E is equal to, from Lenz's law, it's now minus d phi by dt. But inductance can also be written as the measure of the change in flux linking a coil due to a change in current through it, multiplied by, obvious, the number of turns through the coil, right? So the larger the inductance of the coil, the larger will be the instantaneous change in flux linking the coil due to instantaneous change in current. So V becomes equal to L di by dt, right? V becomes equal to L d phi by dt. L is called N d phi by di. V becomes equal to L di by dt. So remember that the voltage induced across your inductor will be determined by the rate of change of the current through the coil. Also, it is determined by the magnitude of the inductance, right, of the coil. So the voltage across the inductor is directly related to the inductance L and instantaneous rate of change of current through the coil. So the greater the rate of change of current, the greater the induced voltage. So if current changes very fast, the induced voltage is very, very large. Right. Now, when we now talk about transients, we are saying we have states that, okay, there's this steady state, the uncharged steady state of our inductor. Then we have the transient period whereby the magnetic field in the inductor is changing. Then we reach another steady state of the charged. So this will be charged. This will be the steady state of the uncharged, right? So what we are talking about is the transient period between T1 and T2. That is the period whereby we start charging to the point when we are fully charged. That is the issue of transients, which we are trying to talk about. So in simple terms, an inductor will oppose changes in current, right? So inductor is initially discharged. It acts like an open circuit. These are the important facts. When an inductor is not charged, right, it acts as an open circuit. It means when the inductor has not been charged, it does not allow current to flow through it, right? That is in this state, okay? Then, looking at the circuit, when the switch is initially closed, we close the switch, close this conduct. The change in current across the inductor immediately induces a voltage that opposes that change, which keeps current near zero. So what are we saying? Initially, there is no current through this. Then you close the circuit. You want current to flow through here and through there, right? The voltage is pushing a current in this direction. Then, from Lenz's law, the induced effect opposes the cause. So what happens? You induce a voltage VL across the inductor, and that voltage tries to push an opposing what? Current from Lenz's law, right? So this will be the induced current, right? and this will be the charging current. Okay? So when you close this switch, you want the current through the inductor to instantaneously get to the charging current. But the inductor will oppose that, such that even if you close the switch, the inductor is initially an open circuit. Why? Because it has induced a maximum voltage across it. Right? So its voltage, if we assume it will be at a certain value, right? Say E. Why do we say E? It's because initially the current I is equal to 0. So this will be like an open circuit. So if you measure between A and B, you get the value of the source E. So it starts at E. The magnetic field is fully developed, and it is that. Then as the magnetic field starts to collapse, right, the voltage across the inductor starts to decrease. As it starts to decrease, then it means some current starts flowing in that direction. So the current will be building slowly and slowly until you get to a steady state whereby the voltage across the inductor is now totally equal to 0. It's now acts as a short circuit, and the voltage is across it is 0. Remember, I said the voltage across a short circuit is equal to 0. Right. So the storage phase is passed and the state condition have been established. Once a period of time equals to 5 time constant is occurred, the current cannot change instantaneously in an inductive network. The inductor takes on the characteristics of an open circuit at the instant of closing the switch. Then the inductor takes on the characteristics of a short circuit when the steady state conditions have been established. That is what I was explaining on that circuit. So what are the charging equation, right? So as current IL increase across the inductor builds up, the voltage across R1 increases. In other words, E should be equal to VR1 plus VL with this loop, right? So as VL decreases, VR1 should increase so that we always have the sum being equal to E, right? So the voltage across the inductor will decrease exponentially given by this expression. VL is equal to E exponent of minus T over tau. Minus T is the time at which you want to determine the voltage across the inductor, and tau is the time constant, right? Time constant given by L over R, right? That is our time constant, L over R, right? Then the current, as the voltage decreases, we say the current will start to increase in this direction. And at any given time t, the current becomes equal to I naught, which is the maximum current when this is a short circuit, right? Multiplied by 1 minus exponent of minus t times over tau. And we said tau is equal to what? L over R, so it becomes minus T R over L. That's where we are getting it from there. Remembering that the time constant tau is equal to L over R. So the maximum current in this case will be equal to I naught over R1 because this will be a short circuit. So it will be just the source divided by the resistance. But then as time proceeds, it will grow exponentially like that. 1 minus exponent of minus t, at the time instance when you want to determine the current, multiplied by the time constant. Time constant, we are talking about the resistor, which is in series with the inductor. That is the one which we use to calculate the time constant. Okay. Let me remove what I was writing here so that it doesn't obstruct what we want to see there. So VL is equal to E exponent of minus tau minus T over tau, which becomes minus T R over L, R1 over L. So we are saying voltage across the inductor decreases or decays exponentially as time proceeds during the charging phase, right? Then the current through the inductor increases exponentially during the charging curve, given the expression I is equal to I naught 1 minus exponent of minus T over tau, which becomes R minus T R over L, right? And also in like manner, the voltage across R1, since the voltage across R1 is given by IL times R, then it means it also increases exponentially in the same manner, but it increases from the maximum value of VR1, right, which is now E 1 minus exponent of minus T over tau. Again, we've already noted that your tau will be equal to your time constant. Okay, so these are the three important equations that you have to take note of when you're dealing with the charging of the inductor. The explanation being that when you change, when you try to establish the current through the inductor current will not increase instantaneously. So if it cannot increase instantaneously, it means it will need some time to build up, and it has an exponential build up for the current and exponential decay for the voltage, which will have been induced when it was a di by dt introduced, right? So when you try to move current from 0 to I naught in a certain time, then the di by dt will be very large, right? But then after that, you've just charged the capacity of the inductor, then slowly the field depreciates, and then the voltage is going down. Then what are the initial values of our scenario, right? So since the current through a coil cannot change instantaneously, the current through a coil will begin the transient phase at initial value established by the network before the switch was closed. So the current will then pass through the transient phase until it reaches a steady state or final level after 5 time constants. So we are saying in all these transient circuits, if a condition reaches 5 time constants, then it reaches its final value. So if you are charging from 0 to the final value, after 5 time constants, you should have reached the maximum value. If you are discharging from the maximum value to the minimum, you should have reached the minimum value of 0 again in 5 time constant. So the inductor will fully charge or fully discharge in one time constant. That is very, very important to take note of. The inductor will fully charge or discharge over one time constant. So the steady state level of the inductor current can be found by substituting its short circuit equivalent, or RL, for practical equivalence, right? So this is an example circuit which we can use. We close this circuit. We try to push a current opposing voltage there. So this is initially open. Then as the field collapses, the voltage decreases, current starts flowing in the circuit until it reaches a maximum when this is now equivalent to a short circuit, right? So currently the inductor cannot change this energy, but the voltage can change. So what you will notice here is that when we introduce a change in the voltage, right? When you introduce a change in the voltage, then the voltage through the inductor went straight from 0 to VL, which is called E. But the current did not change. The current, we have to wait and build exponentially. So at T is called 0, the inductor adds an open circuit. In other words, at T is called 0, IL is equal to 0, VL is equal to E. These are our initial conditions, right? Then voltage across R1 is also equal to 0, so there's no current flowing. Then the voltage across L is equal to the source voltage as soon as the switch is closed. That's why it's called E. At T is equal to 0, the inductor voltage decreases and the current starts to increase. So T is equal to 0, E should now be equal to minus VL minus VR. But then VL is equal to L di by dt. And VR is equal to IR. Then it means E minus L di by dt, which is this one, minus IR should be equal to 0. And IL is equal to I. And using calculus, it can be shown that IL is equal to E over R, 1 minus S minus T over L over R, which is our time constant, which is called I max, 1 minus X minus T, L over R, which is again our time constant tau is described earlier on. So L over R is our time constant for our RL circuit. And then VR is called E 1 minus X minus T over tau. VL is called E X minus T over tau. Why? Because the voltage across the inductor will start to decrease as we go towards the next steady state condition. Then after 5 time constants, we are going to the fully charged scenario. Then voltage across the inductor is now equal to 0. That's another steady state after fully charging, discharging, sorry. Then IL is called E over R. In VR, will now be equal to E because this is no longer, this is now equal to 0. So you realize that in one time constant, it will rise to about 0.63, the maximum value. Second time constant, 0.86. Third time constant, 0.95. 0.98, 0.993, we can approximate that it has reached the maximum value IM after 5 time constants, right? That is why we say it's fully charged over that. But you realize that this will actually never reach IM as long as the higher resolution calculator, it will continue giving you values 99999 something. That's why it was agreed that they reach that value, we are saying it's fully charged in that situation, right? Then the voltage across the inductor will be decreasing as we go also. One time constant is 0 minus 0.36 or 37, 0.13, 0.049, 0.013, 0.007. After 5 time constant, we can approximate that it has reached 0, though we know that the exponential expression will not reach 0, but it will go to that minimum. So as an example, find the mathematical expression for the transient behavior of IL and VL for the circuit after closing the switch. Then sketch the resultant curves. Right, so we have our E called 50, R1 2 kilo ohm, L 4 henries, right? So we first have to calculate our time constant tau, which is L over R1, which is called 2 milliseconds. That is one of the first very important parameter, our time constant. Then maximum current, again, it's very important, E over R. Remember, we reach maximum current when we fully charge our inductor. So that gives us 25 milliamps. That was our IM or our I naught. Then VL becomes equal to 50, that is E, exponent of minus T over tau. That is straightforward. So when the circuit is at steady state, the voltage and the current reach their final values and stop changing. There's no change in current in the circuit, so the inductor has 0 voltage induced across it. Inductor current will be steady. That's why we reach a state value. The inductor then looks like a short circuit. I think I have explained this. Then the rate at which an inductor charges depends on R and L, which is now our time constant, L over R. Transients can be considered to last for 5 time constants. I've explained when this is a rise and this is a drop. So we're saying after 5 time constants, we can assume that we are there. Right. Example. In the circuit below, the switch is initially open and conditions are at steady state. So if the switch is initially open, we know that the voltage across the inductor is also equal to 0. Current is equal to 0. We only have E. Then after the switch is shut, determine how long it will take for the inductor to reach steady state condition. Write the equation for VL and IL and sketch the transients diagram, then find the energy stored in the inductor. So charging, we have L over R first. I naught 25 milliamps, we've calculated that. The expression for the current, we substitute for I naught, we substitute for tau, and everything remains. That will be the mathematical expression for the current. You just substitute for the maximum current and the time constant. VL, for VL, you substitute for the source voltage and the time constant only. That gives you the mathematical expression for that, or the equation for the voltage across the inductor. Then energy stored in the inductor is equal to 1 over 2 L multiplied by the current through the inductor squared. That's the formula for energy stored in the inductor. Right? You see almost similar equation for capacitors. So here we substitute, we know our L, we know our I, right? So the maximum energy stored will be at maximum current, so it should be about 1.5 millijoules. So what happens if we now interrupt the current in an inductive circuit? When the switch is opened in an RL circuit, energy is released in a short time. This may create a large voltage. Induced voltage is called an inductive kick. Opening an inductive circuit may cause voltage spikes in thousands of volt range. Remember, I said L di by dt. So if di by dt is very large, then that means the voltage can be very large. Okay. So switch flashovers are general and desirable. They can be controlled with proper engineering design. These large voltages can be useful. Such an example is automotive ignition system. So when people talk about the coil in the ignition, they are just talking about an inductor. So in simple terms, it's just a controlled spark that ignites our fuel, right? So you close your circuit, it can be a spark. You open your circuit quickly, there can be a spark. But also, if this is done in a controlled way, that can be used in our automotive starter circuits. So in RL circuit, the energy is stored in form of a magnetic field established by the current through the coil. An isolated inductor cannot continue to store energy since the absence of the closed path would cause the current to drop, releasing the energy stored in the form of magnetic field. That's the difference between an inductor and a capacitor. A capacitor can store the energy for some time, but once you disconnect an inductor, the magnetic field will collapse and the current becomes equal to 0. Then the magnetic field will release the energy, right? So that's the difference. Since an inductor stores energy in a magnetic field, it cannot store it when it is disconnected. Then here we're talking about charging. Then we're also talking about the discharging or the release phase, right? So analyzing the RL circuit in the same manner as the RC circuit, when a switch is closed, the voltage across the resistor R2 is E volts, and the RL branch will respond in the change in current di by dt. Using the equation, V is called L di by dt, and this will establish a voltage, high voltage VL. I think we explained this. Now, when we close this circuit, right? When you close that circuit, at steady state, okay? At steady state, this becomes a short circuit. So the voltage across this becomes E, and the voltage across that becomes also what? Becomes equal to E. Okay? So when you now open the circuit, what will happen? There's no source. So in other words, you are trying to cut this current from I0 to 0. In no time. And the inductor will not allow it. Okay? The inductor will not allow that to happen. So it will oppose that, and the current IL will still continue to flow through that path. Right. So after storage phase is passed, the steady-state conditions are established. The switch can be opened without sparking effect or rapid discharge due to the resistor R2. The voltage L across the inductor will reverse polarity. So, like I said, the voltage across here will now be E, and this will also be equal to E. So even if you open, there is no current to flow through that, and there is no sparking. So that will be basically the purpose of that resistor. Okay? Then VL was now equal to 0. Right? Okay. Then you open the circuit. You want this current to to go to 0 from whatever value it was, that change will have a response from the inductor. In the inductor, will establish a voltage across it that is opposite the change, right? So VL becomes equal minus VR1 plus VR2. VL becomes equal to minus I1 R1 plus I2 R2. I think that is straightforward from our Kirchhoff's voltage law. Then writing these expressions, right? I1 and I2, since it's the same circuit now we've opened, I1 and I2 are there. IL, because it's the same current flowing, right? Then our IL will be equal to E over R1. We're talking about the instant of removing the source or opening the switch. So it goes E over that, R1 plus R2. So if you rewrite this, you put this over R1, this over R1, you find out that VL becomes equal to minus 1 plus R2 over R1 times E. So that will be the initial voltage across the inductor. You can see that it's now different. It's no longer E. It's now 1 plus R2 over R1 multiplied by E. In other words, that voltage is greater than E in all instances, but opposite. So VL decays to 0 as the magnetic field collapses and energy is released through the resistors. VL is equal to minus VI exponent of minus T over tau slash, right? Tau slash is now a U. Tau, remember we now have two resistors in series with our circuit, R1 and R2. VI becomes the initial voltage, which I was explaining, given by that expression. Then tau becomes equal to L over RT, where now RT is called R1 plus R2 because now they are now in series. They are both now in series with the inductor when we remove the source. Okay. Then IL becomes called E over R1, exponent of minus T over tau slash. Again, it's still tau slash. Why would we have E over R1? Because that was the maximum current flowing through the circuit before it was opened. So what changes is the initial value of the voltage. That is the one which is now determined by R1 and R2. VR1 becomes equal to E exponent of minus T over tau, because VR1 was now equal to E when we removed the source. So that was the initial value of VR1 was equal to E. Then VR2 becomes equal to R2 over R1 exponent of minus T over tau slash, right? That's our R2. So if you look at it, that's why we have 1 plus R2 over R1 times exponent of that 4 using the initial values here, right? Then, assuming that is initially fully charged with a constant time constant of with a constant 100 milliamp current, it acts like a short circuit. When the switch is opened, the inductor will immediately induce a voltage to keep the 100 milliamp current constant. Kirchhoff's voltage law can be used to calculate this induced voltage. Notice the polarity of the induced voltage, right? So what I was explaining now is that we remove our source. This is now our initial condition, right? So VR1 becomes called I naught R1 because the maximum current was flowing there, right? Then VR2 becomes called I naught R2 because at 0, 0, the current is at maximum. In times R2, you realize that the voltage is very, very large, right? Then VL, with the voltage across the inductor, becomes equal to 1,100 volts, but it was just produced by that initial circuit that we're talking about. And then our current now will be moving from a negative towards 0, right? To be moving from a negative towards 0. But remember, now you have this current flowing, right? And because it's now like an induced effect, your inductor will now induce a polarity that should assist the continued flow of current. Remember, we said the induced voltage decides that it opposes the cause. So when you open this one, you are trying to say that IL should stop flowing and should be 0. Then the inductor will respond using Lenz's law by producing a polarity that stops IL from reducing to 0. That's why the voltage of the inductor in the discharge phase is now aiding the current. But now, since the field is collapsing, the voltage will be going to 0. Instead, the energy is reduced, the inductor voltage across the inductor drops, right? And also the voltage across the resistors as iron decreases. It means this voltage is also, because they are IR, they also start to decrease. Okay? Then our I arrow will be equal to I naught x1 minus t. This is the new tau, right? For our discharge phase, the value of the tau will change. But for VL is using the old value of tau. So voltages and currents in discharging circuit, they will change exponentially over time. I think they will be reducing over time, running to 0. Current voltage also is now a different polarity. After I remove the said, it will be positive and negative on that side, right? Then after 5 time constants, discharge is complete, right? The discharge will be complete. And so everything will be going down to 0, like that. Right? So you realize that in the discharge, VL goes to 0, IL goes to 0, VR1 goes to 0, VR2 goes to 0 in that situation. So let's use an example again. The circuit shown below has been in operation with the switch shut for a long time. What we say for a long time, we are saying the time is greater than 5 time constants. In other words, we are saying we have reached the steady-state conditions. And what are the state conditions in our inductor circuit? VL will be 0, IL will be at a maximum. VR1 will be equal to E, VR2 will be equal to E. Those are our steady-state conditions. Then how long will it take for the inductor to discharge? It's simple. You want the new time constant. Once you get the new time constant, multiply it by 5. Right? That becomes your time required to reach its steady-state conditions. For that one is a simple one. Write the discharge equation for VL and IL. So I naught E over R1. I naught x1 minus t over tau. Then VL becomes called VR1 plus VR2, which is called I naught R1 times plus I naught R2, and you get 125 volts. See the difference. This is coming from there. So when we're charging, it charged to E, but when you are discharging, it starts at a larger voltage, because of what I was explaining before when you open the switch. VLT is equal to minus E exponent of minus T over tau, which is called 125. Remember, our E now is our new initial value, 125, multiplied by the time T over the time constant. That becomes the expression for VL, and that one is the expression for IL. Lastly, we look at inductors in series. This one is very simple. When inductors are in series, they are treated like resistors in series. When inductors are in parallel, they are treated like resistors in parallel. That's all I can say about that. Everything else is very simple. Okay. Set condition, an inductor can be replaced by a short circuit in a DC circuit after a period of time greater than the 5-time constant have passed. Assuming that all the currents and voltages have reached the final values, the current through each inductor can be found by replacing each inductor with a short circuit. Energy stored in an inductor, 1/2 arrow I maximum squared in joules. In other words, the inductor will store energy when connected to the circuit. So that's all we have for our inductors and transients. So using these same explanations, you can go back and look at the capacitor networks. You see that they are very, very similar, except that for a capacitor, the voltage is the one which cannot change instantaneously. For inductor, the voltage can change instantaneously. Then for a capacitor, the current can change instantaneously. For inductor, the current cannot change instantaneously. So that's all for today. I'll stop the recording. And if anyone has questions, they can ask.